So you had like all of Thanksgiving to think about polar coordinates and not turkeys. So how do you graph? How do you graph 2, 5 pi quarters? Because you couldn't do much of that take-home quiz yet because lots of new stuff on that we didn't get to. So how do you graph 2 5 pi quarters? Go out 2 and around 5 pi quarters. What quadrant are you going to end up in? The third. So out 2, 1, 2, right to there. And then around 5 pi quarters puts me right there. Okay. How about the next one? How do you graph -3 5 pi 6?
Go out 3 and go out 5 pi 6 backwards?
Go out 3, not quite. Go out 3, 1, 2, 3, and then around 5 pi 6 puts you right there.
But then you go backwards.
And then you reflect over which puts you there. So here's the unreflected point, right? And then your final answer is that point there.
I found it easier to reflect first.
Yes, we also discussed the fact that you could reflect first, which would put you over here, and then you could go 5 pi 6, which puts you in the same place. That's also fine, okay? Both things are fine. All right, how about -4? Oh, and just for kicks, what's another way to write that point without the -3? +3 and then negative pi over 6. What if you had to use a positive angle?
11 pi over 6.
11 pi over 6. 1 pi 6 shy of 2 pi, right? Okay. All right, -4, -5 pi 6. So I just prefer this way. 1, 2, 3, out 4, back 5 pi 6, right? And then reflect up to that point. Okay, so here's be consistent in my color scheme. Here's the unreflected point. There's the final answer, right? Write that with +4 and pi 6. Okay, so plotting points, okay? All right, another skill you have to do today's lesson is graphing sine and cosine, because we're going to do a lot of stuff with this right now. So what is the interval for which you get sort of like the main picture of what happens with both sine and cosine? 0 to 2 pi. So where does sine start? Starts at 0. And then you divide the interval up into sort of 4 parts between pi halves, pi, 3 pi halves, 2 pi. And then what does sine do first?
Goes to the origin?
Goes to the origin, and then what does it do after that? Goes up to 1. And then it goes
Back to the origin?
back down.
Back to 0, sorry?
Yep, that's fine. And then at 3 pi halves, where does it go? -1, and then up to, exactly. So there is y equals sine of x. Okay. How about cosine? Pretty similar, you still go from 0 to 2 pi. So I always start by dividing my interval up into those 4 pieces. And where does cosine begin?
1.
And then it goes down to,
Zilch.
down to,
1.
back up to,
Zilch.
and,
1.
yep. Okay. So we can graph those pictures, yes? Okay, you also have to know how to graph, so there's y equals cosine of x. What happens if you were asked to graph sine of 2x? It goes how fast compared to regular sine? Twice as fast? Which means how many full oscillations does it do between 0 and 2 pi? Does 2. So that means the first oscillation is complete by pi. Does that make sense? So if I was graphing sine of 2x, it starts at 0, but at pi quarters it's up at 1, right? Pi halves were at 0, 3 pi quarters were at -1 and then back up to 0. The kicker it does two oscillations in 0 to 2 pi, right? How many oscillations would sine of 3x do within that interval? It'd do 3.
Three.
How long would each of them be?
2 pi thirds.
Does that make sense? He's right. 2 pi thirds? So if it does, so one period is 2 pi for the standard sort of sine curve, right? If you go through 3 of them in 2 pi, each one is 2 pi thirds wide, okay? And then how about sine of x over 2? How would that change?
It'd be 4 pi.
It'd go half as fast, and it would take 4 pi to go through the whole cycle. Okay. So far the curves you've seen on stuff like this have been easy things. Like, for example, what did the equation r equals 2 describe? Do you remember?
Circle of radius of 2.
Circle with r equals 2. What did theta equals pi quarters represent, roughly speaking? It was a line. You think that's every point that's a consistent angle, right? I think that's actually the line y equals x. Okay. And then we also had stuff like r equals to cosecant of theta, which was weird, but not hard, because you just remembered that cosecant is 1 over sine. And so therefore r sine theta is 2, and this was just our expression for y, right? So that's the stuff you've seen so far. We're gonna now, and so if you were asked to graph r equals 2 cosecant theta, it's a horizontal line. If you were asked to graph theta equals pi quarters, it's a line with slope 1 going through the origin, right? If you're asked to graph r equals 2, it's a circle of radius 2. What we're gonna graph now is stuff that's a little bit, so r equals 1 plus cosine theta. And the way to do this is to first sketch this as if you were in Cartesian coordinates, and then translate that into polars. Okay, so let's just first sketch this thing in Cartesian coordinates. So my x-axis is now the theta axis, my y-axis is the r-axis. Okay. And I need to draw just regular cosine before I start. So 1, -1. So regular cosine begins at 1, down to 0.
Would draw regular cosine or regular 1 plus cosine?
This right now is just r equals cosine theta. I'm just slow. If you graph 1 plus cosine theta, how does that change? Just shifts it up 1. If you can go straight to that, I have no problem with this. It begins at 2. By pi halves, we're at 1. By pi, we're at 0. 3 pi halves, we're at 1. And by 2 pi, we're back at 2. Okay. So there's r equals 1 plus cosine theta. And this picture gives you a way to visualize all the points you're graphing. You're going to graph all these points r comma theta, where r is your distance and theta is your angle. It's like at this very, very, very first point right here, that's the point where your r is 2. What's your angle? 0. So that means you're right there. You probably should be writing this down. If you're, okay. And then what happens as you go to pi halves? What happens to your radii? They get smaller, and they specifically decrease to, at pi halves, what's your radius now? 1. And then how about by pi? What's happened to your radii?
0.
It's gone down to 0. And a kind of kicker thing is, between pi halves and pi, your radii are all less than 1. Does that make sense? Which means they're going to stay inside this little inner circle here. So it does something like this. I got kind of picky with some students last semester who were really sloppy, and they drew this picture this way. You see why that's kind of a problem? You draw it in red, and you can explain to me why that's bad.
It's kind of like a heart shape.
They did stuff like this. Why is that bad?
Because it goes past the 1.
because the radius goes past 1, radius is always less than 1 on that interval. So that, what they did there was bad, and I no longer have an eraser. Preppy. Okay, so we'll white that out. Okay, so what happens now between pi and 3 pi halves?
It does reflect it.
Yeah, it's kind of reflected. See how the radii starts off at 0 and goes back up to 1? So whatever happened here is going to happen down there as well. Goes back up. And then what happens as you go up to 2 pi?
Goes back up to 2.
Goes back up. And it makes a sort of heart-shaped thing.
It's a cardioid.
It's called a cardioid, exactly.
So it's around at the end instead of point.
Yep, it shouldn't be pointy. It should be rounded at the end. But, you know, my inferior drawing skills.
I don't know, if you knew the origin of that shape, you wouldn't think it's a heart.
No, you wouldn't. And it isn't supposed to be pointy on the end. It's just my picture that makes it look like it is. Does that make sense?
Yeah.
Like it's supposed to be smooth. And also just indicate what direction your curve is traced with an arrow. We asked for that on the quiz, but the homework doesn't ask for that. So just make sure you know that you start here. And then also what's going to happen as this pattern in my 1 plus cosine theta continues. I'm just going to repeatedly trace this picture. Okay. All right, so does everybody get how I took this thing into this thing? Okay.
Why like, you know, at the top of the heart, where it curves like that, why isn't that just a straight line?
Why isn't it? Because this is sort of smoothly, you're asking like, why isn't it something like
Yeah,
why isn't it like that?
Yeah.
Because that would say that for all of the angles, like, oh God, what would that even mean? For all of the angles in here, radius is 0,
So when
and the
we're
radius is
drawing-
only 0 at that one point.
Okay, so when we're drawing, we should make a point and curve them all.
Yeah, exactly. It is definitely curved, and you see how this is kind of continuously decreasing down with the radius being 0, and if you were to draw these points like as rays, you see how those kind of like get smaller and smaller and smaller? They start off pretty big out here, and then they decrease. Does that make sense? Yeah. So what you described something that would decrease really abruptly, which isn't the case, at least not for stuff like this. Okay, let's try another one. All right, 1 minus 2 sine theta. All right, this one's a little bit more tricky, but it's also a cardioid. And because I'm slow, I'm just going to start by graphing -2 sine theta and then doing the upshift by 1. Is that okay? Okay, does the period of sine change at all?
No.
No, it's still 0. It's one cycle between 0 and 2 pi. Okay, 1, 2, 1, 2. Starts at 0 by pi halves at -2. Pi at 0, pi halves at 2. Okay. And then if I graph 1 minus 2 sine theta, how do I shift this picture?
Go up by 1.
Just go up by 1. So at an angle of 0, we're at 1. Pi halves, we're at -1. Pi, we're at 2. 3 pi halves at 3. 2 pi, we're up at 1.
Pi, we're at 1 as well.
Say that again?
When we're at pi, we're at 1 as well.
Oh, yeah, when you're at pi, you're at 1 as well. Yep. Yep, yep. Move that 1 point up 2. Oh. Okay. It probably would also be useful to know what those points are. Does that make sense? That's where the radius is going to be 0. How would you find those? Say solving 0 equals 1 minus 2 sine theta. So that's 2 sine theta is 1, or sine theta is a half. So at what thetas is that going to happen? Pi 6, yep. And 5 pi 6. And do those make sense with your picture? Because pi 6 certainly is between 0 and pi halves, right? Okay, so I'm going to color coordinate this. I think it really helps. So let's do the first portion in black. So at an angle of 0, what's our radius? 1. So we start right there. Okay, this first ray, that's theta equals pi over 6, right? What's happened when you get to that angle? Your radius has gone down to what? 0. So what happens is you do that kind of business. Your radius goes down to nothing. Okay, now the next part's the tricky part. Between there and there, let's just graph this pi halves point. That's the point -1 pi over 2, isn't it? So if you were to plot that point, how would you plot it? You'd go up, well, you're on pi halves and up 1, right? And then you would reflect. So that ends up down here. Does that make sense? Okay. It does loop around. So here's what happens. This part, right there, that's like being graphed like this, but this point gets reflected down there. This point gets reflected down there. Because the radius is negative. Like all throughout there, the radius is negative, right? So what happens is this part of the curve gets traced as the whole negative reflecting business.
If you absolute value, is that how you get a supercardioid shape?
Oh, I'd have to think more about that one, okay? All right, how about from pi halves back up to 5 pi 6? Yeah, it loops back around. So it does this kind of business. And that's the hardest part of this. The rest isn't very difficult. So what happens between, when you got into pi, what is your radius now? 1. So you've done this kind of business, right? What happens when you get to 3 pi over 2?
That's 3.
Radius is 3. And then what happens as you go back to 2 pi?
And just loop back up.
Loops back down to 1.
That is how you get a supercardioid shape.
I don't know what that, I don't know what a supercardioid shape is,
It's
so.
kind of like a mushroom where that end is reflected out.
Oh, okay, yeah.
Yeah.
That makes sense, because that would just reflect this bit up. Do you guys, so if you absolute value this curve,
Yeah.
this part would get reflected up here, and then this loop would just be up there, right? I mean, because there would be no reflecting because it wouldn't be negative anymore. Does that make sense?
Yeah, it's used in microphones because you get rejection on this.
Oh, really?
Yeah.
Okay.
That's
I
what
didn't,
it is.
I didn't know that. Cool. Okay. Alrighty. So do you understand how the whole negative R thing works here? Okay, that's the trickiest part. If you can get that, the rest is really not that bad. Let's try another one. R equals 3 sine 2 theta. This is the first curve that we have where the period is not 2 pi anymore, right? But graphing your function in Cartesian coordinates, like going from 0 to 2 pi, will pretty much always get enough of a picture. Occasionally you'll get more than you need, okay? So if you are to graph 3 sine of 2 theta between 0 and 2 pi, how many oscillations does sine go through? No, not 3. 2. What does the 3 do? Stretch, because the amplitude, it makes the graph taller. Okay, so 1 oscillation is done by pi. And this is 3, -3. So pi over 2, pi over 4, 3 pi 4. 3 pi halves, 5 pi quarters. Okay, so I go through one cycle between 0 and pi. Where does my sine curve start? 0. When is 3 sine 2 theta up at 3? By pi fourths. When's it down to 0? When's it at negative 3? And then back up to 0 by pi, right? And then it does it twice. Yeah, it does one more time. So back up to 3 by 5 pi quarters, down to 0 by 3 pi halves, negative 3 by 7 pi quarters, and back up by 2 pi. Okay. Let's sketch this bit first. So where does my picture start? So right there at the origin, right? Because I'm at angle 0, radius 0. When I've reached pi quarters, by the way, which of those rays is pi quarters?
Second up.
This middle one. There's theta equals pi quarters. So by the time I get to pi quarters, I'm out at 1, 2, 3. So I've increased out to 3.
So if it was decreasing, that'd be the other.
Say that again?
If it was decreasing, the curve would be on top of the other.
Yes, if you had like negative 3 sine of 2 theta, it's going to change the direction probably. It will change the direction. It might also change which part of this you start on. What happens as you get to pi halves? Your radius goes back down. This definitely is symmetric. It's just my inability to draw something symmetric that's going on here. So it has this kind of like petal-shaped thing. Okay.
Do the same thing for the negative.
Yeah, so now this one. That point there is negative 3 pi quarters. The point down at the lowest point is the easiest one to graph. So if you were to graph that point, you would rotate 3 pi quarters and then you would reflect down to here. And you'd be tracing this bit, which would reflect down to this bit. So there's the next part. And then what happens?
You missed it, you're on the wrong.
Oh, I'm on the right. Yes, sorry. Should be right there. Yes? Okay, there we go. And the width does matter, but it's hard to get it exact because these don't have very nice numbers. The general shape is more important. Then you go back down to 0.
Then you're in the third quadrant of positive values.
Yep, then between pi and 3 pi halves, that puts you in quadrant 3 because here's 5 pi quarters. And you trace out this part of the curve.
Then you're in the fourth is negative 4.
And then you're in the fourth, yep. And trace out that part. And I always find that this point's the nice, easy one to plot. Like plotting negative 3, 7 pi quarters isn't so bad, right? Okay, so that ended up being, and then what would happen if you graphed more of 3 sine 2 theta? You just go again. And just to be clear, this one first, this one second, this one third, and that one fourth, right? That was the order those things were graphed. because it's kind of hard to just follow the arrows. There was a test question I gave once, I think it was a final, where I asked people to number those things in the order they went. It isn't always the case that this is the order, just for this curve it is. If I made it 3 cosine of 2 theta, it would be a little bit different. Okay.
And they're usually a smooth drawing mesh.
And they're usually a smooth, yeah, they're not like pointy
You don't
or,
wanna, like, change direction.
no, other curves will do that, but nothing like this will do that. So notice that 2 theta, there were how many petals? 4. Okay, so if I gave you 3 sine of 4 theta, besides wanting to hurt me, it's gonna have how many petals?
5.
8, okay.
That's the odd number stuff.
Yeah, this is a little bit different. So here's something funny happens with 2 cosine of 3 theta. So first of all, let's just start, it'll be clear what funny thing happens once we get graphing. So how many oscillations does cosine of 3 theta go through in 2 pi? 3, right? So that means 1 is completed by 2 pi thirds, right? 1 is the next one completed by 4 pi thirds. Does that make sense? Okay. And now divide the interval from 0 to 2 pi thirds into 4 even pieces. I find it easiest to half and then half again. So what's halfway between 0 and 2 pi thirds? Pi thirds. And then what's halfway there? Does that make sense? So then you're counting by 6. You have 1/6, 2/6. What comes next? 3/6. And how does 3/6 reduce? Pi halves, right? So 1/6, 2/6, 3/6, 4/6, 5/6, 6/6 is pi, right? 7/6, 8/6, 9/6 is 3 pi over 2, right? 10/6 is 5 pi thirds.
Row 6 compared to 7.
Because 7, 8, 9.
No, because 7 was a registered 6 offender.
I like mine better. Mine is more appropriate for class. Okay. So now our curve, since it's cosine and it's 2 cosine 3 theta, where does it start? 2. By pi 6 we cross. Pi thirds we're at -2, right? Pi halves back at 0, 2 pi thirds back at 2. Okay. So here is theta, there is r. On your homework, you're asked to graph things both in Cartesian and polar coordinates. So like part of your homework is showing this graph, and always go from 0 to 2 pi. Okay? All right. So first let's graph this a little bit. So at an angle of 0, where do you start? 2. And in this case, you can get the width of the petals down pretty well. By pi 6th, you're down to 0, right?
Yes.
Which means you don't want to go past that pi over 6 line. Does that make sense? Okay. So there's the first part. Okay, the questions were where's the next bit can end up. So this point right there is -2 pi thirds. Let's graph that point first. So you go out 2 and around pi thirds, which is right there, right? So you reflect down, and what quadrant are you in now? Third. So we have this point. And all of these points are kind of doing this thing before reflection, right? So they're going to reflect over here. Oops. Okay.
Continuing the smooth line.
Continuing the smooth curve, yep.
Curve.
And then what happens as you go up to pi halves?
It goes back once again.
your radii decrease to 0. And that's because you're sort of on this part, and those points are reflecting down to that part. And that negative part's the hardest part. Okay, now from pi halves to 2 pi thirds, 2 pi thirds is this right there, right? So you go up to 2, and then by 5 pi 6, you're down to 0. And this last bit, do you see how that's these points are going to reflect and make those? Okay. And you're like, but I have so much more curve left. And yeah, this rest of the curve is going to trace it over again. So this part, pi 7 pi 6 will trace this part. That's going to be this stuff gets reflected onto that. The 7 pi 6, that's going to trace this bit again. So it turns out that when you have an odd number in there, that going from 0 to 2 pi traces the curve twice. That always happens. Like if I gave you r equaled 2 cosine of 5 theta, that would have 5 petals. So
You get the same number of petals as the.
you get the same number of petals as this, whereas the other one,
You get twice.
you get twice as many. Does that make sense? Okay. And whether it's sine or cosine kind of changes like where that how that curve is rotated and where it begins. Like if I graphed 2 sine of 3 theta, it would look very similar, just be shifted a little bit, kind of like spun around. Oh, and let's just kind of number. This was part 1, right? And then this was 2, 3, and then it kind of finished up at the end, right? Okay. Whew. All right, so you'll do a lot more practicing graphing stuff at recitation. Now we're going to move on to doing calculus with these things. So it's actually not that bad. So we have this equation. R is a function of theta, like R is sine theta, R is cosine theta, stuff like that. R is, I don't know, 2 sine 3 theta, things like that. So these are the parameterized equations. And I want you to find the slope of the tangent line to that stuff. And think back to what we did back in section 10.2. If I had x equals f of t, y equals g of t, dy dx was dy dt over dx dt, right? We're going to use the exact same idea, except for the variable now is theta. And our r is equal to some function, like it might actually be a function like 3 cosine theta or something like that. So here is the derivative. And you have to memorize this, but I personally don't memorize it. I just remember how to derive it, and I re-derive it every single time because that's how it works for me. So x is r cosine theta, y is r sine theta. That much you know because it's basically the same thing as the unit circle, right? Okay. So dy dx is dy d theta over dx d theta. That's the same thing as if we had t's, right? So to differentiate y, because r could be a function, you have to use the product rule. So the derivative of y is going to be dr d theta times sine theta plus r times cosine theta. And that's because r could be a function of something. So r is, something that, some equation like the ones we just had.
Okay, so R is the variable and theta is the constant?
R is like y and theta is like x in some sense.
No.
Yeah, r is a function of theta. And the reason we choose to have it as r equals versus theta equals is that this parameterization involves thetas. Does that make sense? So you have to have theta in both functions.
Yeah.
And a lot of the equations we've been given have been things like r equals 2 cosine of 3 theta, right? In that case, r is a function of something, right?
Yeah.
Okay. What is dx d theta going to be using the product rule?
Dr d theta cosine theta minus r sine.
Good. Dr d theta cosine theta minus r sine theta. So to find the derivative, you take the equation that you're given and you plug it into this. Does that make sense? Okay. All right. So I'm going to do one? Okay. Here's a funny one. R equals 1 over theta. Anyhow. So what is dr d theta going to be anyway? We'll just get that first. So r is equal to theta to the negative first, right? So what's dr d theta?
Negative 1 over theta squared.
Negative 1 theta to the negative 2, or negative 1 over theta squared. Yep. Okay. So then dy dx is dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta, right, from above? So what goes in for dr d theta? And what goes in for r? Yep, 1 over theta. Okay. So now at theta equals pi, your slope is going to equal. So plug in theta for pi. In the numerator, we have negative 1 over pi squared sine of pi plus 1 over pi cosine pi. Should have done this before, not after Thanksgiving. Negative 1 over pi squared cosine pi minus 1 over pi.
Talk of pi is making me depressed.
Well, you should have gotten lots of pi over the weekend. Okay, certain pieces of that, so they're okay with how I got that formula? You can show less work if you want, because it's pretty obvious that certain pieces in this expression are going to be 0, right? In particular, which pieces are 0? The ones that involve signs. This part is 0, and this part is 0, right? So what we end up with in our numerator is negative 1 over pi. Is that right? You buy that? Because cosine of pi is negative 1, right? In the denominator, what do we end up with? Is it positive or negative? Positive 1 over pi squared, right? And it's really, really bad math grammar, like using the wrong there in a sentence to leave fractions over fractions. So that's the same thing as negative 1 over pi times pi squared over 1, which is negative pi. That's what you have right now because you owe your friend a pie for Thanksgiving. Okay. And already. I know. One more. It makes you scared when there's a whole page, doesn't it? So graph the curve r equals 1 plus cosine theta, and then find the points on the curve where the tangent is either horizontal or vertical. So,
Didn't we already graph that?
I don't know if we graphed 1 plus cosine or 1 plus sine, but you might have graphed 1 plus cosine. Did we? Okay.
Do it again.
Well, it won't hurt. This is not a very hard one, right? 2 pi, So the first one we did, and it had no funky reflecting things going on, right? Starts off at 2. By pi halves, we're at 0, right? By pi, we're back at 0.
It's just like
Yep. It's this heart-shaped thing. Okay. Now, figuring out where the tangent is horizontal and vertical, what's that going to involve? The derivative, right? Okay. So first of all, dr d theta is negative sine theta, right? That would tell us where we have horizontal and vertical tangents in regular coordinates, Cartesians. We don't care about Cartesians, we care about polars. So you need to find dy dx, which is, oh goodness, dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta. And these can get a little tricky. Okay.
How did you find the RD theta?
Just take the derivative of that. Yeah, just take the derivative of that with respect to theta. It's like basic calc 1.
Yeah.
Yep. Okay. So now let's just plug in the stuff we know and be very, very careful. So I'm going to plug in negative sine theta for dr d theta. Is everyone okay if I say negative sine squared theta right there? Okay. Plus r, which is
1 plus cosine theta.
all that times cosine theta, right? Okay, over negative sine theta cosine theta, right? Minus 1 plus cosine theta times sine theta. Okay. So that's negative sine squared theta plus cosine theta plus cosine squared theta over, is there a greatest common factor in the bottom? I could take out a negative, right? And I also could take out what? Sine. I think just sine, not cosine, because of the whole one thing right there. So if I say negative sine, and then I'd have cosine theta plus 1 plus cosine theta. Do you buy that? Everyone okay with this so far? Yeah? Okay, now the denominator's not super tricky. The denominator is, yeah, negative sine theta, 2 cosine theta plus 1. And here the problem is what you're going to do with this is you want to figure out where the numerator is 0 and where the denominator is 0, right? And the denominator, not so bad, right? The numerator, well, we'll just go ahead and leave it and we'll talk about how to solve it just separately. Okay. No, I lied. I want to do this now. Okay, I'm so sorry. I think it does help to do it first. Well, no, it definitely does. Okay, so with this guy, if you were trying to solve this equal to 0, the problem is you have sines and cosines, right? It'd be easier if you just had one like either sine or cosine, not both. So you have two options. You can change the sine squared into cosine squared, or you can change the cosine squared into sine squared. And one of those is a good idea, one's a bad idea. So why is changing cosine squared into sine squared a bad idea? Because you have another cosine there. It's better if they're all the same function. So change the sine squared into cosine squared. Like not just like make it cosine squared, because that's not right. What do? Sine squared is equal to 1 minus cosine squared.
Can't you just make it all cosine by doing the double angle and just make it
Oh, well, there is a
cosine
double
2
angle
theta?
entity, yeah, you can do that. I didn't solve it that way, and I'm not sure that that's, because then you're gonna end up with a cosine of 2 theta, I think. I don't think that's gonna help. I mean, maybe you solved, because then you have like, if you can figure out where cosine of 2 theta is equal to cosine theta, you can do it that way. I don't think it's easier, because my way is gonna factor.
Yeah.
But your way will theoretically work, like it's not wrong. Okay, like it does work.
It's just a little more work.
I think it is a little bit harder though.
No, I mean, it's just, you're just pretty much finding where that equals 0. It's cosine 2 theta and cosine theta. If the theta is pi over 2 or 3 pi over 2, it'll be a 0 nonetheless.
Okay. I do believe you, but I'm gonna just go this way because I know this works, and we'll still see at the end if your answers match, okay? Okay, so you got 2 cosine squared theta plus cosine theta minus 1, do you agree with that? Over negative sine theta 2 cosine theta plus 1. And then one more step, and I swear I'll stop. Factor the numerator. Yeah.
Could you, at that step, couldn't you separate them out and say like the numerator equals 0 and the denominator equals 0?
Yeah, you could. I'm just going to factor first, but you could. So if you factor the numerator, what do you get? You got 2 cosine theta and one factor that's cosine theta, right? And I think, is the first one minus 1 or plus 1? I got minus 1 plus 1, is that right? I think it is, right? Because you get 2 cosine theta times cosine theta gives you the cosine squared, right? And then 2 cosine times 1 is positive 2 cosine. Minus a cosine just makes singular cosine. Okay. And now we can do what Mary Kate said. When do we have horizontal tangents? And the numerator is 0. 2 cosine theta minus 1 equals 0, or cosine theta plus 1 equals 0. So that's cosine theta is a half. And at just between 0 and 2 pi, what angles does that happen? Pi thirds. And I think 5 pi thirds.
Yeah.
Because it's over here and over there, right? How about cosine theta equaling negative 1? Pi. Okay, how about vertical?
0.
Negative sine, oops, sorry. Your vertical when negative sine theta is 0. That actually corresponds to 2 points in 0 to 2 pi, doesn't it?
Yeah.
What are they?
0 pi.
0 and pi. And then also if 2 cosine theta plus 1 is 0, so that's cosine theta is negative a half. What angles are those?
2 pi thirds.
Mm-hmm.
And 4 pi thirds.
Mm-hmm.
Yeah.
Okay. And I'll pause and let you catch up because I know this is kind of crazy. It's a lot of work. And there's one slight problem that won't happen on every problem, but it happens on this one. So what is the slight issue that you see? There's one point that landed in both categories. Does that make sense?
Pi.
Do you see how pi ended up giving both a horizontal tangent and a vertical one? And it only does one, it doesn't do both. So any points that only landed in one place are fine. Okay, so these two are certainly horizontals, And you might have to, for your web assign, also figure out what the R value is, but how do you do that? Just plug it into the equation, right? Which ones are vertical for sure? Also 0, right? Okay, so those are all good. It's just pi that's a little bit funky, and you're not sure what's happening at pi. So how you deal with, and this won't come up on every single question, it just comes up on some of them, okay? How you deal with that is you find the limit as, not x, sorry, theta goes to that pi from either side. So I'm just going to do limit as theta goes to pi from the left of 2 cosine theta minus 1 cosine theta plus 1 over negative sine theta 2 cosine theta plus 1. And you can go at pi from the left or from the right, it doesn't matter, just pick one of them. Or you can just go with regular pi, it really isn't that important. Now, and that what's the thing that's inside my limit? What did I put there? It's just the derivative, right?
Yeah.
I'm figuring out what happens to my derivative as I get close to pi. If this is equal to 0, then you have what kind of tangent? Horizontal. If this is equal to some kind of infinity, then you have a vertical tangent. Okay, that's kind of what's going to happen with this. And the kicker with this thing is that you can break the limit up into a product of limits. And you do this a little bit at the beginning of Calculus 1, but not very often after that. So looking at this ratio, there are certain parts that don't go to 0. Which part in the numerator doesn't go to 0 when you plug in pi? Does 2 cosine theta minus 1 go to 0 when you put in pi? No, okay. Does cosine theta plus 1 go to 0 when you plug in pi? Okay. And then in the denominator, which part goes to 0 when you plug in pi? The sign, so put that one over here. And then which part doesn't go to 0? This part. And you should learn that, like, this is why you didn't like derivatives, because this rule for products work for limits, but not for derivatives. With this first thing, can you now just plug in pi?
Sure.
Sure. I think the numerator ends up being -3. The denominator ends up being almost -1, right? What rule do you have to use on this next part? L'Hopital's. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine, right? I think this ends up giving you, now can you plug in theta equals pi in this limit? And you get, you get 0. That's going to be 3 times 0 or 0. So at theta equals pi, is the tangent horizontal or vertical? Horizontal. Does that seem to make sense with our picture?
Yeah.
Yeah. Okay, that's crazy. I know, it's insane. So, I don't think the homework question that you have is this tricky. Yeah.
Why does it make sense to try to take a derivative if it's a corner in that direction?
Yeah, it is a corner.
It's a good question. Never thought about it. Because it is a corner. I think it's because even though it's a corner, the slopes from both sides match. I think that the rules for corners are different in this graphing system. Because as you, yeah, it has to do with how you approach the point. I mean, because you're approaching the point like this, and that's flattening out to 0, and like this, and that's flattening out to 0. So I think in this case, corners, you can still find derivatives at them.
If you think about it
If you think about it, like
like there's.
If you think about really making, if you think about making a smaller and smaller angle, and what happens to the slopes is your angles get closer and closer to zero, the slopes approach zero from both sides as the angles decrease, which doesn't happen in regular calculus.